Hi everyone, let's move on to Module 5 now, which is uniform circular motion. Uniform circular motion is motion in a circle of fixed radius r at constant speed v. So it looks something like this, where we have an object moving in a circle or a part of a circular path of fixed radius. So just two definitions I want to go over before we go on. One is the period. The period of the motion, we've seen this before in the lab, has symbol capital T and is measured in seconds. And this is the time that it takes for one cycle of the motion. So for one revolution of the circle in this case. So the time it takes the object to go around the circle once is the period. Then we have the frequency, which has a symbol of lowercase f. It's inversely related to the period through 1 over the period. The frequency is the number of cycles of the motion that occur per second or per unit time. So in this case, it's the number of full circles that the object moves through per unit time. And its unit is over here. It's 1 second inverse, or 1 per second, since we have period in the denominator here. And this is defined to be a hertz. So 1 hertz is 1 per second, and we'll measure frequency in hertz. There's a simple relationship that can be used to find the speed of an object moving in uniform circular motion. Recall that for a constant speed, we have distance over time. So the distance traveled for this object in one cycle of the motion is the circumference of the circle. The circumference of the circle is 2 pi r, and then we know that the time it takes to move through one cycle of the motion is the period t. So the speed of an object in uniform circular motion, which remains constant, is 2 pi r over the period. We could also replace the period, 1 over the period, by the frequency and write the speed in terms of the frequency as 2 pi rf. Okay, now I want to answer a few questions about uniform circular motion. Okay, so the first question is an object in uniform circular motion accelerating? And the answer is yes, it is. It has a non-zero acceleration. And the reason is that, remember, an acceleration is a change in velocity per unit time. Though the speed is constant for this object, its velocity is not constant, right? The direction of the velocity vector is changing as it moves throughout the circle. So this direction change must mean that there is a net force acting on the object, and thus there is a non-zero acceleration, and the acceleration is what's causing it to change direction. So anytime an object is moving at a constant speed, if its direction is changing, it's still accelerating. All right, next, what is the direction of the velocity vector? Well, I've drawn it here. At any point in the circle where the object is moving, the velocity will be tangent to the circle. Tangent to the circle means that it's perpendicular at 90 degrees to the radius at that point. So it looks like this, where it's tangent at any point along the line. Using this fact, we can kind of answer part 3. It's hard to see here, but if you were to do a scale diagram using the magnitude of the velocity as well and the direction of the tangent vectors, if you were to subtract them, you would find that the centripetal acceleration, which is the change in velocity per unit time, is directed towards the center of the circle. So at any point, our acceleration is towards the center of the circle along this radial line. And we'll see in the next section that this is because the net force is always directed towards the center of the circle. To answer number 4, when an object is accelerating in uniform circular motion, we call this the centripetal acceleration. So it's labeled with a C to mean centripetal here. And the relationship is that AC equals V squared over R, V meaning the speed in meters per second, and R the radius of the motion in meters. So we can always calculate the centripetal acceleration using this short expression. It can be proved by either using a derivative or similar triangles. I'll leave that out for now, but you can look in the textbook to see more about that. And remember that the direction of the centripetal acceleration is always towards the center of the circle at any point. I've just included one more thing. Since we know that the speed is 2 pi r over the period, you could plug this in, and then you can find this expression for the acceleration in terms of the period if you didn't want to maybe calculate the speed first, or this gives you a way to go directly between acceleration and the period. Okay, let's look at some examples. Example 1, determine the centripetal acceleration of the moon about the Earth. The distance from the Earth to the moon is 3.84 times 10 to the 8 meters, and the period of the moon's orbit is 273 days. All right, so to start, we're going to need SI units. So let's convert that period of the moon into seconds. So there's 24 hours in one day times 3,600 seconds in 1 hour, which gives 2.36 times 10 to the 7 seconds. All right, so we want to eventually find our centripetal acceleration, which is v squared over r. So to do that, we can find the speed first. We could plug it in here, or we can just calculate this number first. So 2 pi times 3.84 times 10 to the 8 meters divided by 2.36 times 10 to the 7 seconds is 102.2 meters per second for the speed of the moon in its orbit. All right, then we can plug that into the centripetal acceleration formula here. So AC will be v squared, 102.2 meters per second squared over 3.84 times 10 to the 8 meters, which is 2.72 times 10 to the negative 5 meters per second squared for that centripetal acceleration. Example 2, a record player rotates at 33.3 rotations per minute, RPM. Find the speed and centripetal acceleration of a penny whose center is placed at A, the rim, r equals 30 centimeters, B, halfway to the spindle, r equals 15 centimeters, and C, the spindle, r equals 0 centimeters. Okay, so this is the record player here, or the record, and we have 3 different locations, A, B, and C. So what happens when this spins is that we have all points on this line rotating at the same frequency, the same rate. But because they each have to travel different distances in the same amount of time, since one rotation is the same for this whole disk, they will each have different speeds and different centripetal accelerations. All right, so we're given a frequency here. RPM is rotations or revolutions per minute. So that means there's 33.3 rotations in 1 minute. So we need to convert that into SI units. So we have 33.3 rotations per minute times 1 minute over 60 seconds, which gives 0.555 rotations per second. Rotations is actually unitless, so this is the same as 1 over seconds, which is a hertz. So we have 0.555 hertz for the frequency of the rotation. We can write the speed for uniform circular motion as 2 pi r over the period, which we can then replace 1 over the period by the frequency. So since we're given the frequency, we can use this form of the speed equation this time, or you could alternatively find the period and then use this one, and we'll get the same result either way. So I'll use this with the frequency, and let's look at A, where we have r equals 30 centimeters, so 0.3 meters. First, the speed, v equals 2 pi rf, is 2 pi 0.3 meters times 0.555 hertz, which is 1.05 meters per second. Then the centripetal acceleration is v squared over r, so that answer 1.05 meters per second squared over 0.30 meters, which is 3.65 meters per second squared. So this outer edge will have the highest speed because it travels the largest distance in that same amount of time. Now if we look at halfway to the spindle, where r is 0.15 meters, we can calculate this again, 2 pi times 0.15 meters times 0.555 hertz, and we get 0.523 meters per second. And you could also notice that the only factor that changed is r. V is proportional to r if we look at this formula, so it should be half of what we found in A, and it is. Okay, then our centripetal acceleration will be 0.523 meters per second squared over 0.15 meters, and this is 1.82 meters per second squared. Lastly, we're looking at the very center of the disk here, so it's everything spinning around that point. And at that point, r is 0. So this means that v, which is 2 pi rf, also must be equal to 0, and then AC is 0 as well. So in fact, that point is not moving, it's stationary at the center of the circle, and we wouldn't say that it's in centripetal motion or uniform circular motion at all, so it doesn't have a centripetal acceleration. So in this example, you can see that the distance to the center on this disk that's uniformly rotating determines its speed and its centripetal acceleration. Example 3, a common concept in science fiction movies is the idea of rotating a space station to produce an apparent or artificial gravity that the station inhabitants will experience. A. In 2001, A Space Odyssey, the space station has a diameter of 560 meters and a period of rotation of 48 seconds. What apparent gravitational field would the inhabitants experience? Okay, so the idea here is that astronauts in space need to experience some kind of artificial gravity. So if there's an astronaut in a space station like this, if the space station is turned in a circle, so then rotated, maybe about this point here as I've drawn, then the acceleration felt by this astronaut will be the centripetal acceleration. So the faster it spins, the greater the acceleration, and the larger the radius, the smaller acceleration. And when adjusted to the right velocity, we can have AC is approximately equal to g, and the idea is that this could simulate the gravity felt on Earth. All right, so let's look at A. Here we have a radius of 280 meters, which is 560 over 2, and a period of 48 seconds. So the speed is 2 pi r over the period. 2 pi times 280 meters over 48 seconds is 36.7 meters per second. And then the centripetal acceleration is v squared over r, so 36.7 meters per second squared over 280 meters gives about 4.8 meters per second squared for the centripetal acceleration. So in the movie, this is not quite equal to g, right? We'd need 9.8. That's about half of the acceleration needed, but if the astronauts are not appearing to be weighted in the same way to the floor, maybe they are experiencing less acceleration, right? Okay, let's look at B. B, in Armageddon, the space station is spun about its axis to produce artificial gravity. Its central module has a diameter of 4.15 meters. 1. What would the period of rotation have to be to produce 1 g of artificial gravity at a 2-meter tall person's feet? And 2. What would the artificial gravity be at the person's head? Okay, so it looks something like this, where the head of the person is near the center of the module. In the first part, the radius is 4.15, the diameter over 2, because we're looking at the person's feet, which is on the outside of the space station here. And we want the acceleration to be equal to 1g, which equals v squared over r. So this means v will be the root of gr. So we can find the speed that way. V is the root of 9.8 meters per second squared times 2.075 meters, which is 4.5 meters per second. So let's see what period is required to produce this. The period is 2 pi r over the speed, so 2 pi 2.075 meters over 4.5 meters per second, so 2.9 seconds. Okay, for part 2, let's see what that period would produce for a centripetal acceleration at the person's head. So the head is actually only making this small circle around the midpoint, so its radius will be smaller, 2.075 meters minus 2 meters, so only 0.075 meters. So this gives a speed of 2 pi times 0.075 meters over the period, 2.9 seconds, which is 0.16 meters per second. And then a centripetal acceleration, I'll put it here, v squared over r, so 0.16 meters per second squared over 0.075 meters, which is 0.34 meters per second squared. So that's a big problem with the idea of this method of artificial gravity, especially for a smaller radius space station, right? There would be a significantly different acceleration felt at the person's feet and at the person's head. Example 4, how fast in RPM must a centrifuge rotate if a particle 7 centimeters from the axis of rotation is to experience an acceleration of 125,000 Gs? Okay, so we have this very high centripetal acceleration of 125,000 Gs. Eventually we want to find the frequency because we're asked how fast in RPM, which is a unit of frequency. So let's start by finding the centripetal acceleration, or using it to find the speed. So we have v equals the root of ac over r, rearranging this, 125,000 Gs, so 125,000 times 9.8 meters per second squared, times r, 0.07 meters. This gives me 293 meters per second. So now we can find the frequency using v equals 2 pi rf. F is v over 2 pi r. 293 meters per second over 2 pi times 0.07 meters, which is 666 hertz. And then converting this into RPM, hertz is 1 per second, so it's a number of something per second. In this case, it's a number of rotations per second. So 666 rotations per second times, we have 60 seconds in 1 minute, and multiplying this gives almost 40,000 RPM, so it rounds to about 40,000 RPM, which is a very, very high rotation rate.